This is the first section of our Homework 6 tutorial, Dummy Variable. In this section, we are going to cover two topics. The first one is the main use of dummy variable for group comparison. By incorporating dummy variables for group membership or interaction terms for group membership with other independent variables, we can better identify what effects, if any, differ across groups. So for example, sometimes we may wonder whether men earn more money than women. Well, there could be many reasons for the fact that men earn more than women. The first hypothesis may be that men earn inherently more than women because of some institutional structures. So we may capture this inherent difference between men's earning and women's earning by using a dummy variable to measure the difference in an intercept. So if men has a higher intercept, it means on average men will earn more money than women. Or we may have another reason, saying that men are better at school, so they tend to have a higher education, a higher level of education than women. So because of their higher level of education, then they earn more money. So in this case, we may have an interaction term between gender and education. And then this dummy variable captures the difference in the slope of education. So if a man has a higher slope of education with respect to salary, then we may say that they earn more through education. And then we can test the hypothesis by looking at the coefficient on the dummy variable. So these are the two ways of using dummy variable to make comparisons between groups or among groups and to see what the difference they make. And the second topic we are going to talk about is what should we do if we have more than two groups. Let's proceed to the first topic first. The first question we are going to look at is question 9.5, group comparison and interpreting dummy variables. So let's consider the model here. So we have salary as the dependent variable and gender and experience as the independent variables. So D is the gender, the dummy variable, and D equals to 1 for male and 0 for female. If we plug in the numbers, we can get the expected salary for female, which is a base group, equals to alpha 1 plus beta times xi, because D equals to 0 for female, so this term drops out from the equation. And if we plug in 1 into the equation, and then we get the expected salary for male, which equals to alpha 1 plus alpha 2 plus beta times xi. And if we compare these two equations, we can see that the difference between a female's expected earning and the male's expected earning is alpha 2. So if alpha 2 turns out to be significant, we say that everything else held constant, the annual salary of male professors is alpha 2 higher than that of female professors. So alpha 2 measures the magnitude of the difference. 1 or 0 may not be the only way to code the dummy variable. We may have other ways to code the dummy variable. Suppose D equals to 1 for female and 2 for male. So in this way, we have female as the base group again. So if we plug in 1 into the model, we get the expected salary for female equals to alpha 1 plus alpha 2 plus beta times xi. And similarly, we plug in 2, we get the expected salary for male. So if we compare those two equations again, we can see the difference is still alpha 2, even though the numbers, the terms change. So if alpha 2 turns out to be significant, we say that everything else held constant, the annual salary of male professors is alpha 2 higher than that of female professors. So this is how we interpret the coefficient of the dummy variables, and it measures the difference between two groups in terms of the dependent variable. Now suppose we change D to D prime, where D prime equals to 1 for female and 0 for male. So in this way, we switched the comparison and the base group. So remember, previously we have 0 for female and 1 for male. And now we switch the numbers, and then we get the male professors become the base group. And then we run a regression of y on d prime and xi. So here we get a new coefficient gamma 2. So in this case, gamma 2 measures the difference between the comparison group and the base group, but we are comparing the female group with the male group. So if alpha 2 in the previous model measures how much male earns more than female, after switching the numbers, gamma 2 in this case will measure how much female earns less than male. So in this way, we can see that the relationship between gamma 2 and alpha 2 is that gamma 2 equals to minus alpha 2. They are the opposite of each other. So whenever we have a model with dummy variables, the first thing that we need to pay attention to is to distinguish which is a base group and which is a comparison group. And most of the time, the coefficient of the dummy variable will capture the difference between those two groups. But we are comparing but what we are compared against is the base group. So if the base group change, then the meaning of the coefficient on the dummy variable will change as well, like what we just mentioned here. So now suppose we have more than two groups, and then we get to the question 9.11. So consider a simplified model from that question. We have the price of a cola as a dependent variable, and then we have the dummy variable d1 as the independent variable, where dummy variable d1 equals to 1 if the cola is from a discount store. It equals to 10 if it is from a chain store, and it equals to 100 if it is from a convenience store. I would say first that this assignment of dummy variables is unusual, and it assumes an arbitrary scale for the categories. So we can see that discount store has the smallest number, and convenience store has the highest number. So if we go up the scale, then it means we are going from discount store to chain store to convenience store. The magnitude of the number doesn't have any meaning, so it's just a scale, an arbitrary scale that we assigned to those three categories. So suppose we get a positive and a significant coefficient beta 1, then it means if we go up the scale, the price of the cola will go up as well. So discount store will have the lowest price and convenience store will have the highest price. And if we get a negative number, it will be the opposite result. But most of the time, we wouldn't assign values to dummy variables in this way, because in this way, so dummy variable becomes a numerical variable, which the meaning seems arbitrary and useless. So alternatively, we would define two dummy variables for those three categories. So let's define S1 and S2, which takes values of either 1 or 0. So we will connect the discount store with S1 equals to 0 and S2 to 0. And when S1 equals to 1 and S2 equals to 0, then we mean the chain store. And when S1 equals to 0 and S2 equals to 1, then it is a convenience store. So if we run a regression of P on the two dummy variables, we can have three cases. So when S1 equals to 0, S2 equals to 0, we get the expected value of expected price of a cola in a discount store. And similarly, we can plug in the numbers and then get the expected price of a cola in those other two stores. And then in this case, we can compare those three equations. We see that here beta 1 captures the difference of the expected price between chain store and discount store, and the beta 2 captures the difference between convenience store and discount store. And then the difference between beta 1 and beta 2 captures the difference between the chain store and the convenience store. So that's how we measure or capture the price difference. It is a better way and a more clear way to get those difference and to compare those three groups. And in general, if we have n groups or categories, we need n-1 dummy variables when there is an intercept. But we need n dummy variables when there's no intercept. So look at this example. So in this example, we have beta 0, which is the intercept, to capture the price for a discount store. So if we don't have beta 1 originally in this model, we would have another S0 to replace it. So in that case, we have three dummy variables for these three categories. So that's what you need to pay attention to when you construct the model. So the last thing we want to talk about is the interaction terms. So we will have question 9.29 as an example. So consider the simplified model from the question. So we have the logged wage income as a dependent variable. We have a dummy variable of education, which is DE2, and equals to 1 if the worker has primary education, and equals to 0 if the worker doesn't have primary education. And DPT, which is another dummy variable, measures whether the person is a permanent worker or not. So if DPT equals to 1, then the worker is a permanent worker. But if DPT is 0, then it means the worker is either a contract worker or a part-time. So he's not permanent. And we have two other additional regressors. Here we should put an error term. I missed it. So because we have an interaction term, we have two dummy variables here. So we have three groups of people to compare. And the first group is workers without primary education. So it is it is when DE2 equals to 0. So when DE2 equals to 0, the second term and the third term will drop out from the equation. So we get the expected wage income for this group of workers. It equals to beta 1 plus beta 4 times H plus beta 5 times D6. And the second group is non-permanent workers with primary education. So now we have primary education, D2 equals to 1, but DPT equals to 0. So plugging in these numbers, we get the expected wage income for this group equals to beta 1 plus beta 2 plus beta 4 times H plus beta 5 times D6. And then the third group is permanent workers with primary education. So D2 equals to 1, DPT equals to 1. So the expected wage income equals to beta 1 plus beta 2 plus beta 3 plus beta 4 times H plus beta 5 times D6. And again, we want to know what's the difference among these three groups. So the first thing that we need to explain is the assumption behind this model. So note that we don't have a term DPT by itself in the model. So most of the time when we have an interaction, we would have at least one term from the interaction to be an independent variable in the regression. So here we have D2 interacted with DPT, and then we have D2 as one independent variable in the regression. We could have 2 and we could have 0, but most of the time we would have we want to have at least one of this term. And by specifying the model in this way, we are assuming that DPT has no effect on wage independent of education. What does that mean? It means if you don't have any education, if you don't have primary education or any education beyond that, then whether becoming a permanent worker doesn't matter. So the effect of being a permanent worker it's only significant when it is interact with the education. So if you don't have education, then these two terms drop out, so DPT has no effect on the wage income. If you have primary education, then if beta 3 is also significant, then it means you can, if you become a permanent worker, then you get additional increase in your wage income. So beta 3 captures the interaction between D2 and DPT, which means the effect of the job type, of the permanent status through education. So it's an effect through education. It's not an independent effect on wage income. So that's because we don't. That's why we don't include DPT in its model, because we are assuming that its effect is only reflected through education. So now let's consider another example where if we cross out D2, then we'll only have the interaction term in the regression. What does this mean? This means we are assuming that education and the job type, which is whether permanent or not, has no effects independent of each other. So if you have either education or permanent job status, it doesn't help you in terms of your wage income. Only when you have both, then you can get you get a premium, like you earn more money through the combination of those two. So if we want to know whether education and the permanent job status work together, we can test this model by looking at the significance of beta 3. So that's how we interpret the coefficient. And the interpretation depends on how we structure the interaction and the dummy variables. So in this question, if you use the data, you can check all the coefficients and see whether they make sense or not, or whether they are significant or not, and whether we should include them or not. So this is the end of this section.